Hello everyone, welcome back to our channel. This is Om and today we are here to discuss about design of one-way slab part 3. So let's recall what we have already studied in part 1 and part 2. So I have explained you the question, then I taught you the first step should be calculate the aspect ratio. Then the next step was how to assume the effective depth. Step 3 was the calculation of overall depth. Step 4 was calculation of effective depth. All these portions, or you can say all these 4 steps, were covered in part 1. Then what we have done in part 2. So in part 2 I have included calculation of dead load on slabs, then calculation of moments, which was step 6. And now what we will do in step 7 and step 8. So that is in today's video, design of slab part 3, we will do step 7 and step 8. Step 7 will be calculation of the main reinforcement, the spacing between the main reinforcement, and then step 8 will be calculation of distributors and the spacing between them. In the design of one-way slab part 4, we will discuss the drawing of the slab. So I think I have explained everything about this. So now let's start. So design of one-way slab part 3. Let's quickly revise the question. So it was a slab of 9 meter into 18.2 meter, which was divided in 5 equal parts by 4 beams of 300 mm thickness with equal spacing. Also, there was a live load of 4 kN per meter square and a dead load of 1.5 kN per meter square, and this dead load was a floor finish and partitions. We used Fe415 steel, M20 grade of concrete, and the rest is discussed in the answer. So first we calculated the aspect ratio. Then using the IS 1456 clause 23.2.1 we assumed the effective depth. Moving on, we calculated the overall depth and then the effective span. So we are doing all our calculation along the shorter effective span. Just you can comment in the comment section why we are taking the shorter effective span in the consideration. After that we calculated the load on slab and the calculation of moments was done. Then we chose the maximum moment. Why the maximum moment and why this negative sign? Like the question is, with this negative sign, how this moment can be the maximum moment? That I have already explained in the design of slab part 2. You can rewatch that video, or if you know the answer then you can comment in the comment section. So today what we are going to do? So today we will move to the step 7. So in step 7 we will calculate the main reinforcement. Main reinforcement. Then what is the formula for main reinforcement? If I would write the formula, then it would be ASD is equal to PT by 100 BD. So first of all we need to calculate PT by 100, and PT by 100 is equal to 0.5 FU divided by FCK whole multiplied by 1 minus root under 1 minus 4.6 mu divided by FCK into BD square. Now we need to know what are all these values. So we will just assume FCK. We are assuming that we are using a M20 grade of concrete. So I can write it as 20 MPa. Then what is Fu? So Fu will be the yield strength of the steel or reinforcement, that is Fy. This is the usual notation for the yield reinforcement. Now we have seen that we are using Fe 415, so I will write it as 415 MPa because the strength of Fe 415 is 415 megapascals. What is B here? So we are assuming a strip of 1 meter along the slab. So B is 1000 mm. Now what is D? D is our effective depth. We have already calculated effective depth in our first video, that was design of slab part 1. So D will be 1. Just have a look. What was our D? So effective depth was 114 mm. So it will be 114 mm. Now our last unknown entity is Mu. So what is Mu? Mu is our maximum moment, and our maximum moment over here is 18.03. So 18.03. I will just ignore the minus sign because I am just using the quantity. Now what's the unit of moment? It's kilonewton meter per meter. So we know values of all the entities on the right hand side, so we can easily calculate what's on the left hand side. So I can write PT divided by 100 is equal to, just remember the formula, 0.5 divided by Fu, which is 415 in our case, divided by FCK, which is 20 in our case, then 1 minus root under 1 minus 4.6 into Mu. In our case it's 8.03, and I will just convert its units, so it will be 8.03 into 10 to the power 6 divided by FCK, which is 20 into B and D square. Now I will calculate this. So now what we need to do, we need to calculate the Asd required. So for that we have a formula. I have already told you the formula of Asd required, which is PT BD by 100, that is PT by 100 multiplied by BD. So what is our PT by 100 that we have calculated from here? It's 4.2 into 10 to the power minus 3. Then B is 1000 and D is 114. Right. Now I will just multiply all the things. So it's 478.8. Yeah. So this is our 478.8 mm square per meter. What is the required spacing for 12 mm dia bar? Required spacing for 12 mm dia bar. So we have a formula for that, which is cross section area of bar into 1000 divided by Asd required. So cross section area of bar was for 12 mm dia, it's 113 into 1000, and what is Asd required? That is 478.8. So it's 1132 478.8. It's 236 mm. So I can just write it as 200 mm because we are providing less spacing than what is required. Now we have three conditions for the required spacing. So required spacing should be the least of, first, what we have calculated here, 236 mm. Second, 3 into effective depth, which is 3 into 114. .342 mm, and then 300 mm. Hence we have the least value as this one. Now this is not so practical, that's why we will write it as 200 mm. So if we are choosing a 12 mm dia bar, then we can provide a bar of 12 mm at a spacing of 200 mm. So we can write it as, hence provide 12T at the rate 200 center to center. Now this was our step 7, so we will move forward to step 8, that is distributors. Now we have a clause (26.5.2.1) in our IS 456 for the distributors, and there it is written that for high grade steel, that is steel grade starting from Fe415, we will take PT as 0.12%. So steel required will be 0.0012 BT, which is equal to 1000 into thickness of the slab, which in our case is 150. So we got 180 mm square per meter. So we can say that required spacing for 10 mm dia bar, like we can take 8 mm dia bar or 10 mm dia bar, anything. So I am just considering 10 mm dia bar over here. So cross section area of 10 mm dia bar is 78.5 mm square. Now we have the formula cross section area of bar into 1000 divided by Asd required. So I will just use this formula here. So my Asd required is 180. Now if you will just go and calculate it, it will be 436.11, which will be approximately equal to 400 mm. So we will again follow the condition for the distributors. So required spacing will be the least of three conditions. First, what we have calculated here, that is 436.11 mm. Second, 5D, which is 5 into effective depth, that is 5 into 114, which is 570 here. And third condition, it should not be less than 450 mm. Now you can know this from the clause 26.3.3b. So you can write it here that it is derived from the clause 26.3.3b. Hence we will use the same format. For the distributors, you have to provide 10 mm dia bar, sorry, you can write it as 10T at the rate, what is our spacing? 400 center to center. This was all about our main reinforcement and the distributors. So if you are finding this video useful, you can hit the like button, and also if you have any kind of suggestion or question, then you can ask in the comment section. Now just a piece of information what we have to do in the next video. So we will move to the drawing. So in this blank space you will find the drawing in the next video. Till then, take care and bye bye.